Today we will discuss about the assignment of linear regression. So in linear regression, we are discussing about an automobile manufacturer who is going to move to a new country and who is looking to sell products in a new country. And for that, in this assignment, for that he wants to know the independent variables on which the dependent variable, that is the price of the car here, depends. So the independent variables here will dictate the price of the car, which is the dependent variable here, and new manufacturer wants to know the exact independent variables on which the price of the car, that is the dependent variable, varies. So we have got the data sheet in where the price of the car is there, and there is other variables: car ID, symboling that depends on insurance, car company, fuel type, aspiration, door number, car body, etc., engine location, wheelbase, car length, width and height, car weight, the engine type, cylinder number, the car weight, engine type, cylinder number, the mileage it gives in highway as well as in city, and the engine size, cylinder number, and the RPM, and the stroke, bore ratio, etc., and how these variables relate to the main variable, to the dependent variable, that is the price. So initially the first part is we have a data sheet which this form, and we load this data sheet. The data is in Excel form, so we load this data into a data frame in R. Here we are using R for the analysis, for the linear regression analysis, and then so we install the packages TIDYR, DPLYR, and car and mass, all these packages to install, and we read the value of car in a data frame, read.csv, car price assignment.csv, so read the value of that, and then after reading we separate the card into two, the brand name and the company name. So next we are interested only in the company name, so we remove the brand name. So for the company name we find that there are next the part is the data cleaning operation. So in data cleaning operation we find that many of the company names are not correct, so for those company names we replace with the correct company name. For example, Mazda is pronounced as Maxda and so on, Toyota spelling is wrong, and other things are there, like Volkswagen is like VW. So we change all these variables to the correct name. That is the one type of company name. Next thing is we have numerical variables as well as the character variables. So character variables here are as factors which have two values. So the thing is we will convert factors which have two labels to numerical variables. How to do it? Factors are like fuel type, which can be diesel or petrol, aspiration, okay, and door number, engine location, all these are character variables, factor variables which have two values. So we convert these character variables having two values to number variables in 1 and 0. So as the linear regression works on numerical variables only, so we convert all factor variables to numerical variables having values as 1 or 0. And then we created the dummy variables. Dummy variables means for those character variables which have more than two values. So for more than two values we convert those values to the dummy variables, wherein for each value there is one numerical value, and in this way we convert the values like car body, drive, wheel, the company name, cylinder number, engine type, fuel system, and all these values which are numerical factor variables, and which are character variables which have more values than 2, and we convert them into dummy variables. So the number of dummy variables is the total number of values which are there minus 1. So in this way we get the dummy variables, and as a result convert all character variables into numerical variables. So next thing is we separate the training and testing data. So 70% of the data we used for training and 30% data is used for testing. So we set seed as 100 and we got two other data sets, 70% data set with the data called training data set, 30% data with data having testing data set. Next we use the LM function in R for the first linear regression model. So first model we created using the LM function, LM price, and with all variables we take and on the training data. Then we applied the step AIC function with both direction. For the step AIC function with both direction, what it does is it converts the variables. It removes the variable. It gives a chart which contains the values of variables having with VIF and p values. Now what is VIF? VIF indicates multicollinearity. Multicollinearity means two values which are showing that they have a relationship with, they are having a same type of correlation with the dependent variable, but actually they are intercorrelated. So their mutual correlation between those two independent variables is high. So what happens is if one variable, the effect of both variables is actually captured by only one variable itself, so another variable out of, so we can keep only one variable out of those two. So the multicollinearity gives the relationship between the two independent variables, and so we use the VIF. If we have high VIF value, that means we can remove that variable as it has a variable, as it has a multicollinear variable with it in the model. Next is p value. P value, if it is less than 0.05, that means it is insignificant. This less than 0.05 means that the null hypothesis is wrong. We have to reject the null hypothesis, and that means here our null hypothesis is the variables is not, the variable does not influence the dependent variable, but if we reject the null hypothesis means the variable influence the dependent variable. So less than 0.05 p value means the variable is not insignificant and we have to take it, but greater than 0.05 probability means the variable, the p value means the variable is not significant and we can neglect it. So in this way, after step AIC, we remove the variables having insignificant p values and high VIF values, and we get the model 2. Next again we calculate the VIF value and remove the VIF values and high VIF values and insignificant p values from model 2, and this way we continue with the variables which are left and finally get to model 10. In model 10 we find that all the independent variables have VIF and p value in the range of our interest, that is the p value is less than 0.05 for everyone and VIF is also less. So that means these variables are independent of each other, and these variables also contribute to the price variable, that is the dependent variable. So we take those variables and we put the predict function. We use the test dataset. So test dataset, on test dataset we use the predict function and we calculate the price of the predicted price of the card for every value of the test dataset. So now again what we do is we calculate the correlation between the predicted price of card and the actual price of the card in the test dataset. So then we get value of R and we R squared it. So R squared gives us the correlation between the actual price of the card as in the test dataset and the predicted price of the card from the test dataset. So from this we find that the value is around 86%, which means that our model is fairly correct and it is fairly more variance is more for it. So it's the same thing we can calculate for 80% training data and 20% test data. With that also we get similar type of result. So what is actually happening is we can say that this model is quite perfect, but for more accurate analysis we must test this model on a data set which is not having on a data set which is like different from this data set, that is for a different time frame data or like that. But actually what happens is the trade-offs between the variance and bias. So if we have a more complex model, it fits the training dataset more correctly. That means it has a large bias, so it has lot of more independent variables, and it fits that data very well with high accuracy. But when we apply that model on a other dataset, it fails to be much accurate. So the model has large bias but small variance. On the other hand, if the variance is small, on the other hand, if the variance is large, that means the data set is does not depend on too much variables, and its accuracy is also low on the training data set, but it maintains its accuracy, or it has more higher accuracy than that when we apply the same data on the test data set. So what happens, that means the bias is low but the variance is high, and so simpler models are better because it is more more because it is better for it to predict values on an other data set than the training data set. Okay, and so another thing is the r square and r squared r square and adjusted r square. So adjusted r square means it imposes a value, it penalty on the, if we introduce a variable which has a high VIF, that is, it introduces a penalty for the introduction of multicollinear variable for a multicollinear independent variable in our model. So as it imposes penalty, so it gives a better accuracy, and also it helps in increasing the model efficiency and its performance on unknown test datasets. So what we get from know here is that a simpler model is a better model, as it is better suited for more accuracy on unknown datasets, as it has small bias and large variance. Thanks.